So we continue on transient heat transfer, and we want to calculate temperatures and heat flows. What we have done is when conductive resistance can be ignored. That's what we have done. That's what is lumped parameter. We now move on to situations where it cannot be ignored, and I'll explain that in just a second. We return to the analogy of travel time from the center of an island to out there in the free water or the bay. This travel time is composed of travel time to the edge of the island, and then from edge of the island to the the free water or the bay. And so this internal travel is analogous to the internal resistance, or the internal travel time is analogous to the internal resistance, where the external travel time is analogous to the external resistance. The first case that we did, that was the lumped parameter, it is the internal transport time. This guy is small. This is the analogy to the diffusion time being small. So lumped parameter is when the heat conduction is very fast from the center to the edge. We are about to do the complementary situation where external travel time, this one is small. And notice that when internal travel time is, when this guy, this distance, or the traveling of this distance is important, then distances matter, meaning if you just need to go to the edge, you'll go the shortest way, right? You would not choose the longest one. And the shape of the object also matters, because that decides how fast you can get to the edge this way or the other direction. And so in other words, for energy transfer, then the shape matters, because that decides which way energy transfer is going to be the easiest. Since the internal resistance is the dominant one, and therefore the shapes matter, then we have to think of different shapes, and we have to do special solutions for each one of them. So of course we start from the simplest situation of a 1D slab. So this is a 1D slab. So here these are the two sides of the slab, and the heat transfer is one dimensional because this is the shortest distance. If we think of a cooling process, so initially let's say the temperature is high, and then you start to cool at the surfaces, then at any given time your center that is farthest away from the surface is going to be warmest. So the temperature profile at any given time can be something like that, but it will keep changing with time. So it is these temperature profiles that we are going to try to get. As time changes, these temperatures all will eventually approach the boundary temperature. So it starts from here and it goes up to here, and this is an intermediate time. Okay, so we need our governing equation, and for that we always start from the most general equation, Now this is heat conduction inside a slab, and it is transient. It is not steady state, it is transient, but it is strictly heat conduction. There is no flow through this distance. So then the flow term, the convection term would go away, and we also do not consider heat generation. So that gives us the governing equation as this one. Now, what are the two boundary conditions? So one of the boundary condition is very simple, that temperature at the edge, temperature at x equal to L is Ts. The other one is I am heating this symmetrically. So it's the same condition here as here. So the temperature profile will always be symmetric. This has to be because the process is symmetric, which means the gradient at the center line will always be equal to 0. So those are the two boundary conditions that we need for the second order derivative in space. But we also need something else. This equation also has a time derivative. So how, if we ask what is the temperature at any time, let's say here, this has to depend on where it started from. So the process has to depend on sort of the initial condition or the kind of the boundary condition in time. So the initial condition is temperature at t equal to 0 is Ti. So this is my governing equation, and these are the three conditions that would be used to now solve this governing equation. So the governing equation and the boundary conditions t at x equal to L at all times is equal to Ts, and del t del x at x equal to 0 all t is equal to 0. These governing equation and boundary conditions are going to be non-dimensionalized now to have insight into the process and also to be able to solve them. So we define these quantities as non-dimensional temperature equal to T minus Ts over Ti minus Ts, and non-dimensional distance is equal to x, the normal distance, over L. So with that, let's try to convert these equations. So you notice from above, del theta del x is equal to 1 over Ti minus Ts del t del x. Okay, and so del square theta del x square is equal to 1 over Ti minus Ts del square t del x square. This is because the Ti minus Ts is a constant. Likewise, for time, del theta del t is equal to 1 over Ti minus Ts del t del t. So if we plug these into the equation right now, so let's see what we get. So we get from here, this one, we're going to plug in for del t and del square t del x square. So del t is equal to this thing times del theta del t. So Ti minus Ts del theta del t is equal to, for del square t del x square, we are going to write ti from here, ti minus ts times del square theta del x square. So these ti minus ts cancels out, and then of course there is an alpha that still needs to be there. So we can further non-dimensionalize this way. We can divide throughout by L square to keep left hand side, right hand side to be the same. And so this alpha I bring to the left hand side. So we write del theta over del alpha t over L square is equal to del square theta del x over L square. In terms of these non-dimensional quantities, then the right hand side is equal to del square theta del x square, and the left hand side, notice that this quantity is also non-dimensional because the left hand side, all of it is non-dimensional because the right hand side is non-dimensional. So since theta is non-dimensional, alpha t over L square has to be non-dimensional, and so I define tau to be alpha t over L square. So this tau is non-dimensional time. So in terms of this new quantity, then I can write del theta del tau is equal to del square theta del x square. So this is my non-dimensional governing equation in terms of non-dimensional temperature, non-dimensional time, and non-dimensional distance. Notice the non-dimensional time has the regular time and L square and alpha. So we're going to see that this quantity alpha t over L square shows up quite often. And so that was the governing equation. How about the boundary condition? So the first one, t at x equal to L and t, so theta at x equal to L, t is equal to ts minus ts over ti minus ts, because at x equal to t equal to ts, so this is equal to 0. In other words, theta at capital X is equal to x over L equal to 1 at all time is equal to 0. Likewise, this one, then del t del x, as we know, del t del x is equal to ti minus ts times del theta del x at x equal to x over L, okay, x equal to x over L, and I can even change this x to be x bar, because that just means I have divided x by x over L, and so I can just divide by L, and then we are fine. And then at all t, so this is equal to 0. That's from this guy here. And so because these are all constant, what this means is del theta del x at x equal to 0. So this is at x equal to L equal to 0, because we're talking about x equal to 0 here. So at x equal to 0 is equal to 0. So this is my one boundary condition now, and this is my other boundary condition. So with these two boundary conditions, we're going to now solve this equation. Okay, so we're going to solve the non-dimensional equation that we just derived, but let's try to recap the equation. So in the dimensional form, this was my equation, and this was changed to the non-dimensional form where it's del theta del tau is equal to del squared theta del x squared, where this capital X is small x over L, and then theta is equal to T minus Ts over Ti minus Ts, and tau is equal to alpha T over L square. Okay, and let's also write the boundary conditions. So at the center it was del T del x at x equal to 0 all time t is equal to 0. So this in non-dimensional form would be del theta over del x at x equal to 0, because capital X is small x over L is equal to 0, and the other boundary condition is t at x equal to 1 at all time is equal to Ts, and that one converts to theta, which is T minus Ts over Ti minus Ts, is equal to theta at x equal to, this is x equal to L, so this would be x, which is given by x over L, so theta at x equal to 1 at all time is equal to 0. So this is my non-dimensional governing equation and boundary condition, and we'll try to solve it. So the way this equation is solved is using what's called separation of variables, and we all see that in our first course in partial differential equation, so you all have seen it somewhere. So we say that theta is made up of two separate functions, one in position only and the other one is time only. So theta equal to f of x, so a function of position only and a function of time only. So this theta, of course, is a function of position and time, that's equal to this. So we have to find this f and g. And so let's plug this back in. And so on the left hand side then, since f is a function of position only, this is a function, so it's a constant when I'm taking the time derivative, so it will be f, and then time derivative would be g prime. That's what we get on the left hand side. And on the right hand side, then this is a derivative with respect to position only. So for the right hand side, then g tau is a constant, and so we only take the derivative of the function x, function f of x. So it's equal to f double prime g. And so from there I can write f double prime over f is equal to g prime over g. So here we use the logic that, look, left hand side is a function of position only and right hand side is a function of time only, and time and position are independent variable. Tau is independent from position x. So functions of two independent variables, if they're equal to each other, then they must be equal to a constant. And let's call that constant to be minus lambda square. Why minus? Because that's when we get a non-trivial solution. If we start with lambda square, we're not going to get any useful solution. So we say this is equal to a negative quantity, lambda square, where lambda is a constant. So from here now we get two equations. So the first one is f double prime is equal to minus lambda square f. Now what kind of a function do we have that if you differentiate twice you get back the same function with a negative sign? This would be a sine or cosine. So then form of f can be written as, since we do not know whether it's sine or cosine, we can leave both of them in there. So we can say this is equal to a times cosine lambda x plus b times sine of lambda x, where we do not know what is a and what is b. So with that function, now we try to use the boundary conditions, these guys, to try to find a and b. So if I use the first one, then f prime x equal to minus lambda a sine lambda x plus b lambda cosine lambda x, this at x equal to 0, this at x equal to 0 is equal to 0. So this gives us, because sine is 0, this gives us b lambda equal to 0, or this gives b equal to 0. So b is already 0. So now I want to use this boundary condition, and that says f of x is, by the way, if I start from theta, so then I will write f, since theta is multiplication f and g, so theta is f at 1 times g at any time tau, this is equal to 0. So g of tau cannot be equal to 0, because then if g of tau is 0, then we plug in here and we get a trivial solution, theta is 0. So this means f at 1 is equal to 0, which means a cosine lambda is equal to 0 by plugging in here. We put in x equal to capital X equal to 1. So then cosine lambda can be any value. Sorry. Okay. So if a cosine lambda equal to 0, then lambda can be any of these values, 2n plus 1 pi over 2. For any value of n, 0, 1, 2, and so on, if we plug that in, then I can satisfy this equation. So lambda can be any of those. Now, so we get somewhere with the f function. Now for the g, we get g prime is equal to minus lambda square g. And what kind of a function, if you differentiate once, you get back the same function? It's not sine cosine, obviously, it's an exponential. So then g is equal to some function. So g is equal to e raised to minus lambda square tau. Okay, So now we got F and we got G. So let's try to put everything together. Sorry, it's getting very messy here, but we are pretty much done. So theta equal to F times G. And now F is what we found was A times cosine lambda, and it can be any of the values. And so because it can be any of the values, A can also be different correspondingly. And then G is equal to E raised to minus lambda n square, because lambda can take any of these values, lambda n square tau. So now we plug these dimensional quantities back in there to get our solution. So T minus Ts over Ti minus Ts is equal to An cosine of 2n plus 1 pi over 2, and there is a x missing, of course. So then times this non-dimensional x would be replaced by x over L times e raised to minus this whole thing 2n plus 1 pi over 2 square times alpha t over L square. Again, my apologies for the small space here. So this is my solution. So for any values of 0 of n equal to 0, 1, or 2, and so on, this equation would be a solution to the original equation with these boundary conditions. Okay. So we skip the rest of the derivation and come to the final solution, which looks like this. Now you can basically see this solution in our textbook or any textbook on heat transfer, mass transfer, diffusion, or any introductory math text that includes partial differential equation. So you can see it there. The difference between what I wrote and the previous slide is this term. We didn't say how we got this, and I'm going to say a little bit more in the next slide. So this is where we had an, and so we now have summation also. So why this summation and so on, I'll just say in a second. You notice the solution has these non-dimensional position and non-dimensional time and non-dimensional temperature. So they all have interpretations. For example, T minus Ts, temperature change is in relation to the boundary temperature, Ts. So T minus Ts is the amount of change that is yet to happen. And so this ratio is the amount of change that is yet to happen or unaccomplished temperature in relation to the possible amount. So Ti minus Ts is the total possible change in temperature because it starts from Ti and goes to Ts. So Ti minus Ts is the total possible temperature. So this is a non-dimensional temperature that represents sort of the unaccomplished fraction. Likewise, the position variable x over L is the fractional distance from the center, and alpha t over L squared is the non-dimensional time. Now, so you can see here that we have a cosine term, right? So cosine comes from the heat equation having the second derivative in position. So the heat equation looks like this, right? Del T is alpha del square T del x square. So we have second derivative in position. That's what led to the cosine term. And the time has a first derivative, and that led to the exponential term. Okay. The next thing is you notice that temperature is a function of position and time. Temperature T is a function of position x and time t. And if we go back to our slide, then t is a function of position, and this function changes with time. So it's a temperature is a function of position, and that function changes with time depending on what time we're talking about. So it starts from initial temperature, and then eventually it reaches the boundary temperature. Then you also notice that this function, this is my cosine function. Okay. And the last thing is, as I already said, that these are the non-dimensional positions and non-dimensional time, alpha t over L square. Okay. Now a little more about why we have the summation term in our solution. So notice that we derived this position variable, the function that shows how temperature varies with position as a cosine term. So when plotted, it will look something like this, part of a cosine function. However, notice that at time t equal to 0, our initial condition is T minus Ts over Ti minus Ts at t equal to 0 is equal to Ti minus Ts over Ti minus Ts is equal to 1. So this is my initial condition. And so if my solution has a form like that, if I take that term, it can never satisfy the initial condition. However, remember, it's not just one cosine term that's my solution. For any value of n, we have different cosine terms. They're all cosine, and then each one is a solution. So if I add two of those terms, then it looks like that, which is a little improvement. If I add 7 of these terms, then it looks like that, which is now getting closer to the initial condition. And so the reason we have a series is from the Fourier's infinite series. If I have a infinite number of terms, and then I add them together, then I would be add them together with the corresponding weights, then I would be able to match the initial condition exactly. So in order to match the initial condition, I need this summation term. Conversely, when I'm not interested in the initial times, I do not need as many terms, and I'm going to show that I need only one term of the series. So let's get the solution, and I'm going to do something very simple. I will plug in value of time at t equal to 30 and plot each term of this series. And then I will plug in time t equal to 600 and then again plot each term of the series. Now, of course, the terms, each term from here to here to here, they drop. But there is a qualitative difference between how the terms are dropping for time t equal to 30 and how they are dropping at time t equal to 600. Do you see that? Whereas for this earlier times, the terms drop, but they drop kind of slowly. Whereas here, the terms drop very, very fast. And this is the reason that for uh, for large values of time, then I don't care about these terms. I only need this guy, because the other terms for different values of n equals 1, n equals 2, n equals 3, they drop off so rapidly that I can keep only the first term in the series. I don't need all of these terms. I just need the first term, n equal to 0. I cannot do this for this case. For this case, this term is quite significant compared to this. So I cannot do it for small values of time, but I can do this for large values of time. So for large values of time, then I just plug in n equal to 0 and I get the first term of the equation, and that's all I need here. So again, to repeat, we learned that the spatial variation is cosine and time variation is exponential, and we skip these other slides that we are going to cover in the lectures, and then come to a simple plotting of the solution that we just derived. So the plot, if we just rewrite the solution that we derived, t minus ts over ti minus ts is equal to 4 over pi cosine pi x over 2l e raised to minus alpha pi over 2l square t. Then if I take natural log of both sides, then the left hand side is natural log of t minus ts over ti minus ts, and this is natural log over this quantity here, and this is an exponential. So if I take natural log, then I get this quantity. Now if I plot on log scale, natural log of t minus ts, and so this is my t minus ts over ti minus ts. I'm going to explain later why we have a different symbol here, t infinity, but for now, ignore that part. Think of t infinity as your ts. Okay, so we have t minus ts over ti minus ts here versus this alpha t over l square, alpha t over l square here. Okay, just a sec. Alpha t over L square. And so then if you plot this quantity, the log and alpha t over L square, then this has the form y equal to ax a plus b, where x is the time variable, alpha t over L square. So then temperature versus time in this semi-log plot, where the y-axis is log of temperature and x-axis is linear but time, alpha t over L square, then you get straight lines. Okay, and what are these used for? So these are called the Heisler charts. So in the days gone by, when computation was harder to do, people just use these charts and read the values. So now you notice that for a given time, if I want to read the temperature, then it depends on what position, right? So if you come to this one, then the temperature is linear with time, that's the ax, and this the intercept really depends on where you are, the position variable x over L. So the curve for temperature versus time depends on which location. So the location variable is n. N is x over L. So at different position, I have a different line because the intercept is different. And this other variable m, which we'll explain soon, so m is equal to k over HL. And if you recall that for this slab, if I have temperature Ts is given at the boundary, this is equivalent to H going to infinity. So M defined as K over HL is equal to 0 in our case right now. So this equation is basically plotted here for different values of x over L or n. So these are different values. So for example, n equal to 0 is this line. So n equal to 0 means x over L equal to 0. So that is at the center. So this is the center, and then it goes farther and farther away. Let's wait to discuss these other plots. Now the case we just did in this transport analogy is when all the time is taken to reach the edge of the island. In other words, the internal resistance is the most significant. So the bus takes much longer than the boat. Okay, now before that, we did the case when the boat takes much longer than the bus. That was our lumped parameter. Now, it doesn't have to be these two extremes, that either the bus takes longer than the boat or the boat takes longer than the bus. They could take about the same time, which means the internal resistance and the external resistance are comparable. That's the case that we're going to do next. So another way to look at this is that the solution to our heat equation, it depends on the boundary conditions. And so the slab that we did, the solution that we did is for this boundary condition. Temperature at the surface is equal to Ts. Now, when temperature is given at the surface, this is equivalent to H going to infinity. So If h is going to infinity, that means 1 over HA, or the convective resistance, is going to 0, which means the conductive resistance is always the one dominating. Um, and so this is equivalent to, or this is analogous to, when the bus takes longer than the boat in transport terms. The other condition would boundary condition can be flux given, and the third one would be convection at the surface. uh, so not h going to infinity, but any value. So we had this convective boundary condition that is true for any value of h. So in terms of the solution now, this conductive resistance and convective resistance can be comparable, or by analogy, the boat and bus times are comparable. So in terms of the solution, then this is the one that we have done, or we just did. For convection at the surface, then the solution can be derived following very similar procedure, just a change of boundary condition. This is shown in the course notes and in the text, the final solution. So the form of this solution and this solution are exactly the same. So this solution can also be plotted just like this one, which I will show in just a second. Um, the other boundary condition, the second boundary condition, flux given, has a very different solution. And that solution is, it's not part of this chart. So then the chart can be used for m equal to 0, because we defined m equal to k over hl. So in this case, since h is infinity, for this case m is 0, and for any other m, we just find the m from k over hl. And this is seen in this plot here. So the one we did, we have done so far, is m equal to 0. Again, m is k over hl, and these are for temperature at the surface. Temperature at x equal to L is Ts, which means if the temperature given boundary condition, this amounts to saying h going to infinity. So if h is going to infinity, then m is equal to 0. So that's why these lines are for m equal to 0. Now for other values of h, when h is not infinity, so here h is not infinity, then of course the solution is going to depend on the values of h. So for any value of h, I can find the m, and I can use the corresponding set of lines. So this is for m equal to 0.5, m equal to 1, and m equal to 2. And now you notice that there can always be any amount of values between m equals 0.5 and m equal to 1. You have to do interpolation. The other point, which I did not mention for this solution either, notice that these plots stop at certain point. It stops here because these solutions are not valid for time t close to 0. Why? Because if time t is close to 0, then I cannot use the one-term solution, which is what these plots are for. Then I have to keep more terms, and the solution will not be a straight line on this log temperature and versus linear time. Okay, so again, to repeat, for the first type of boundary condition, we use these set of charts that are m equal to 0. And the third type of boundary condition where it's any h, I just use the corresponding um, uh, set of lines for that particular m value. Now, and the second kind of boundary condition for flux equal to 0, that's not part of this chart. Moving on to other coordinate system, cylindrical and spherical, the same separation of variables technique work for this system, and one gets series solutions that are analogous. We are not going to do them. We're not going to derive them. They are available in our text. The solutions are available in our text and in any typical text on heat transfer, and full derivations are available in graduate texts on heat transfer. We will simply use these charts. So if they are analogous, they can also be put in a chart form, like the one for slab. The charts for the slab, they were functions of m, n, and this non-dimensional time alpha t over L square, which is called the Fourier number. Okay, so m is k over hl and n is x over L and so on for the slab. The analogous quantities in cylindrical coordinate would be k, the same k, thermal conductivity, h, the same h outside. The characteristic length was L here, and that's replaced by the radius of the cylinder. The same way for a sphere, then it's k over hr, where r is the radius of sphere. Likewise, the n values, instead of x over L, which is non-dimensional distance from the center, this is non-dimensional radius. And then this is also non-dimensional radius. So n values are that way. And then FO, instead of alpha t over L square, where L is the half length of the slab, it's alpha t over r square for the radius of cylinder, and then alpha t over r square, where r is the radius of the sphere. Okay, so here is a quick look at these charts. So this is a quick look at the chart for cylinder, and this is the one for sphere. When surface temperature is given, then you have this m equal to 0, as we discussed. So this corresponds to T equal to Ts, or H going to infinity. Otherwise, you calculate the m and then use the corresponding set of lines. And you do the same thing for sphere. This is for h goes to infinity, and then these guys are for any h. Any h. So this is for any h. Okay. So that means we now have a way to calculate temperatures at any point and at any time for a cylinder, for a long cylinder where only the radius matters. Long cylinder means it's only the radius matters. And then for a sphere where the radius of the sphere matters. So we can do this for cylinder and sphere, and we have already seen how to do the same for a slab. So that concludes getting solutions for slab, cylinder, and sphere for when temperature is a function of position and time.